In this video, we're going to look at the synthesis of fatty acids. This is one of nature's most remarkable synthetic schemes. It's all based upon acetyl coenzyme A. Everything's going to be built from these acetyl groups delivered by coenzyme A. Now, this, of course, is a thioester, and let's just review thioesters a little bit. Thioesters are relatively acidic compared to normal esters. They're more susceptible to nucleophiles, and of course the sulfur is a great leaving group. Of course, this is all due to the fact that there's very little resonance between the carbonyl and the sulfur, making it simply more reactive. Now, how could nature make this even more reactive? Well, it could do the same kind of trick that we've been doing all semester. We can add a beta carbonyl. Beta carbonyl, of course, will make things much more acidic, and of course, potential loss of CO2, a decarboxylation, can give an energy burst to drive further reactions. So how would nature put a carbon dioxide onto the methyl group of the acetyl coenzyme A? Well, it uses a molecule called biotin, and this biotin can actually capture and carry CO2. The way this works is we start by attaching the coenzyme biotin, it's also called vitamin B7, to an enzyme called acetyl coenzyme A carboxylase. And so we've got it attached, it's over here. Now what we do is we do a little acid-base chemistry, and of course this all be taken care of in an enzyme, so enzymes can play around with acids and bases at the same time, something you can't really do in solution. But the carbonyl picks up a proton at the same time as the NH delivers a proton to the S-, and this gives you essentially the nitrogen analog of an enol. As you can imagine, that nitrogen is quite nucleophilic. That nucleophilic nitrogen can actually react with this very strange acid anhydride up here. This is an mixed acid anhydride between carbonic acid and phosphoric acid. And this nitrogen lone pair can simply come up here, attack the carbon of the carbonyl, kick out the phosphate group, and lo and behold, we've picked up a CO2. Now this CO2 is there to be delivered to the acetyl coenzyme A. And the way this works is at first the enzyme forms an enolate of the ester. This enolate, of course, is now nucleophilic, and it attacks the carbon of the carbonyl here, kicks out the rest of the biotin, restoring it to its natural place, and we've just made this new molecule, malonyl coenzyme A. And of course, you remember the malonic acid synthesis for what we did earlier this year. This looks an awful lot like that substrate. This one happens to be an ester on one end and an acid on the other, but all the ideas are there. So this malonyl coenzyme A, along with the acetyl coenzyme A, are going to be our two really important synthetic parts. And the way we're going to build up a fatty acid is we're going to start with an acetyl coenzyme A, and then we're going to add to that various malonyl coenzyme A molecules. And it just depends on the size of the acid will require different numbers of malonyl coenzyme A units. And so both of these compounds will get attached to a carrier protein, which is called acyl carrier protein. And this is just basically doing a transesterification. The thioester moves from the coenzyme A over to this protein. And so we get both of these transferred over. And these, as we see, we're going to do more of these things as we're going along. We have to do some nomenclature here. We call the acetyl coenzyme A the primer, because this turns out that this is going to be the end carbon. It's going to prime the whole system. And then these malonyl units are going to extend the chain. So we're going to have a primer. There's only one primer in a given synthesis, but there can be any number of extenders. So a primer and an extender. Okay, so how does this work? Well, here's our malonyl system. There's the acyl group. The first thing is basically just a decarboxylation, and this very readily forms an enolate, and it gives you a big energy kick. This enolate comes and attacks the carbonyl, and you get a big energy boost from that CO2, and you form a very classic tetrahedral intermediate over here. And this is all, of course, attached to this synthase enzyme. Now, the tetrahedral intermediate acts just the way you expect it to do. It kicks out the best leaving group, which of course is going to be the S- here. So that gets kicked out, okay, and you form our first intermediate here, where basically what we've done is we've taken the original acetyl group and we've extended it by another acetyl group. Well, fatty acids, of course, though, don't have all these carbonyls on them. We got to get rid of these excess carbonyls. There's only going to be one in a final product. So what do? Well, we reduce one of the carbonyls and to an alcohol. And what the reducing agent is NADPH. We talked about NADPH earlier, and to remind you what it is, it's this strange pyridine compound here, where this pyridinium ion here can pick up a hydride and then deliver it to another system. So this pyridinium system here can pick up a hydride down here at the 4 position to the nitrogen and form a compound which will very readily give up that hydride. So you can either add the H- or you deliver an H- depending on which way you go. And so it's basically a great reducing agent, or it can turn around. You can extract a proton and a hydride and go back to the carbonyl. So you can use an oxidizing agent as well. So it works both ways. And hydride abstraction and delivery, that's the name of the game. And basically what's happening here is that the electrons of the nitrogen just come back to restore aromaticity, delivering that hydride to the carbonyl carbon. At the same time, the oxygen would be picking up a proton. So that's the main idea of reducing an alcohol. Now, as we look at these things, the difference, remember there are 2 of these. There's NADPH and NAD+. And the difference is down here, this X group here is either a simple hydrogen, an NAD+. It has a phosphate here, an NADP+. Now, generally, when you bring in the phosphorus, you get an extra negative charge, which means that reductions are most likely, in quotes, going to use NADPH because of the extra negative charge. Oxidations will most likely use NAD+. But it turns out both of those molecules are used, and this most likely is just giving you the most likely. Anyway, that's a reducing agent. So now we got the OH on here, but we still have to get rid of that oxygen. So the next step is simply a loss of water. And you know this happens very readily from the chemistry that we did earlier this term, is when you have hydroxyl group beta to a carbonyl, it's very easy to do that elimination. But now that we've got a double bond, fatty acids are all single bonds, so what we have to do is another reduction. And again, now we use NADPH plus a proton. So we're doing the equivalent of a hydrogen addition. The hydride from the NADPH, the proton from an acid, it's the equivalent of H2. And again, now how would this work? Well, it's basically a conjugate addition from the NADPH. So the hydride adds to the 4 position. You basically pick up a proton, and you reduce that double bond. Now here we've now made a 4-carbon ester out of a 2-carbon ester. So we extended it by 2 carbons. But fatty acids we're talking about tend to be long ones. They're not just 4-carbon ones. They're quite long, and up in the teens, maybe the 20s, numbers of atoms. So what do? Well, what we do is we take this molecule, and the enzyme takes it, and it shoves it back up here to the beginning, and it goes through the whole machinery again. So I'm going to change the slide, and you'll see this 2-carbon unit becomes now a 4-carbon unit as a starting material. So now when we do the whole synthesis, we're going to use another mole of the extender, form a new enolate. That enolate will attack the carbonyl again, get the new 4-coordinate intermediate, do the kick out the S- from the synthase. Here's our new substrate. Now we got to get rid of this carbonyl. We do the exact same thing. We reduce it to the alcohol. We dehydrate. We get our double bond. We reduce the double bond, and now we have 6 carbons. Well, this could get boring pretty fast, drawing it all out, but basically you can just imagine, do this 5 more times. That gives us palmitic acid, which is a 16-carbon fatty acid. And this is where it stops. It's essentially like the enzyme only has room to do this, actually, 7 times. Okay, it started at 2 carbons, it went to 16, and it's got as big as it can go. So what's really neat about this is that all the enzymes involved in this process are assembled into this one large macro molecule, whereas these various enzyme subunits, which are separate proteins, are all bind together in this big complex. You can read about this in the fatty acid synthase article of the Wikipedia. And you can look around here, there's all these things are labeled, and if we just look at them one at a time, is that we start by this acyl carrier protein, which just delivered the original acyl group which came, of course, originally from the acetyl coenzyme A. So this is, you can think of this as just a kind of a handle which is swinging out here in the breeze. The next thing it does, it goes to MAT, and this basically sets everything up for the reaction of the malonyl group. It binds the malonyl group, gets everything set up. That's the unit up here. That's the next enzyme. Then the actual synthesis takes place using the ketoacyl ACP synthase. This is the one where it actually forms that tetrahedral intermediate, kicks everything out. The next process, if you remember, was the reduction of the ketone. So ketoacyl ACP reductase. This is KR. This is unit number 3 over here. What's next? Dehydrating. It goes up here. Notice these things aren't next to each other, which is, I find kind of interesting. But this basically, this arm is swinging these molecules around, doing each piece that it needs to do. We then reduce the double bond. This is the enoyl coenzyme A reductase. This is unit number 5. And then the final unit would be this thioesterase, and this would be used at the very end to convert the final thioester into to the free carboxylic acid, so we release everything. So all this machinery works together. Here are the initials of each of those subunits, and you just simply go through each of these little steps at a time. Each one has its own enzyme, and the molecule goes around here any number of times. Well, not any number of times, up to 7 times to get to palmitic acid. You could make shorter acids by not doing all the steps. Now, the overall product of this thing is palmitic acid, okay? And palmitic acid is this long carboxylic acid here, 16 carbons. And what it came from was one original unit of the primer, okay? This is the original acyl coenzyme A, and then 7 extenders. Of course, these were made from the acyl coenzyme A, picking up carbon dioxide using that biotin method. And so altogether you would have had to have 8 of the acyl coenzyme A's, but 7 of them, of course, were converted to the malonyl unit. So your total stoichiometry here is you start with 8 of the coenzyme A, acyl coenzyme A groups. You needed 7 CO2s. You needed 14 moles of NADP plus. Why 14? Because you have to do 2 reductions in each round. One for the carbonyl, one for the double bond. And so that's the overall stoichiometry. So this gets you to the 16 carbon unit, where here these very first 2 carbons were the primer. And then you had 7 other units which come from the extender. Okay, now what if you want something longer than 16 carbons? Because there are naturally occurring fatty acids with like 18, 20, 22 carbons. How did that work? Well, what it does is there's another enzyme system which looks very much like the one we just discussed, except it's just evolved to accommodate larger molecules. And the way that works, it starts with the palmitic coenzyme A. In other words, this product of the first one gets attached to coenzyme A, and this then does everything that we did before, except now this is the primer. So, for example, arachidonic acid, which is a C20 species, you start with a primer. You start with 16, and then you add 2 more units. You need 4 moles of NADPH, 4 protons, and various enzymes to get this up to the 20 carbon atom species. So that is how you do the bigger ones. If you wanted a 22 carbon one, you of course would would have to use 3 extenders and so on. And what we're going to find in what we talk about next, we're going to get into the area of what's called polyketide chemistry, is that you can vary in various systems, to various plants, various other organisms, bacteria, whatever, use various kinds of primers and other extenders as well, is that you can actually use special extenders with substituents in the central carbon here. So, but that's it for now. We've made our fatty acids. I hope you found it very exciting.